Well, we looked much earlier about the definition of a sequence converging to some number, and we stated that definition, and we also then stated the negation of that statement, what it means for that sequence not to converge to that given number. Well, we're going to do the same thing with limits of functions now. The definition, using very few words, just using symbols, what it means for the limit of f of x as x approaches the number a is equal to the real number L. What that means is that for every value of epsilon, every positive number epsilon, you can find a delta, there exists a delta, such that this is true. And all this means is, this just means that x is in the domain of the function. If it's not, you're not even allowed to plug it into the function. So it says that for all values of x that are close to a, and specifically within a distance delta of a, and not specifically equal to x. So if you're close, but not equal to a, that means that the height of the function at that value of x is very close to the limit L, defined over here. In other words, the distance from f of x to L is less than epsilon. So now let's negate that. We will, in the next few examples, at least once have to prove that the function doesn't exist as x approaches some particular value. And actually, we'll see a function that is defined over all the real numbers, so the domain is all real numbers, yet the limit doesn't exist at any particular real number. Okay, so what does this mean? The limit of f of x as x goes to a is not equal to the real number L, means, anybody remember how I start this? We're negating this sentence, that statement. Say again?
There exists.
Exactly right. For every epsilon, it doesn't work. There exists one, which really means there exists more than one, but we can find one. There exists an epsilon greater than 0. Want to keep going, Maddie?
There exists an epsilon.
You could put such that, but I'm just putting a comma there.
Oh, okay. Such that something with delta.
Yep, just
Still there exists.
no. Remember, for every means, if you're negating it, means if this says for every epsilon something is true, the negation is going to be there exists an epsilon where the rest is false. So this is saying that there exists a delta greater than 0. Well, we're going to say for every delta greater than 0, it's false. And now we need to simply negate what is in parentheses. So instead of saying for every x that is close to a and not equal to a, we're going to say there exists an x. Again, I'm going to be precise here and make sure that x is in the domain. And just like I did here, I'll put a comma there. Now somebody negate this statement for me. It's an implication. It's like P implies Q. How do you negate an implication? When is an implication false? First one is true, and the second one is false. Because the implication says if this is true, then this is true. When is it false? You find a case, well, this is true, but that's false. So all we have to say is that this part is true, and this part is false. So 0 less than x minus a less than delta, just leave it exactly the same. So whenever x is very close to a, within delta of a, but not equal to it, remember, we've got there exists. This x exists, and this is false. So maybe I could use the word and, I'll just put a comma there. It says f of x minus L greater than or equal to epsilon. So that's the negation of the definition of what it means for the function to have a limit at a. This one does not, it's not equal to L if this is true.